you very much. So I hope you can hear me. I have a bit of a throat problem, but I will try to, I hope I will be understandable with the microphone. So thanks to everyone who's organizing this school for inviting me. And it's a pleasure to be here. So I'm going to talk about systems that are long-range interactions and that are of Riesz interaction nature. So, so the main interaction we want to consider, is it okay with the sound? Yes? It's okay. Depends on the parameter S. And it's basically it's the norm or the distance to the power minus S, and you divide by S for some sort of normalization which is convenient. So that works for S different from 0. And you can consider that there's a sort of limit of that when S goes to 0, which is minus log. So if you want, when you sort of look at the leading order of this thing, when S goes to 0, you find minus log. Okay, so this can be considered as sort of degeneration of this inverse power interaction. Okay, so there's two regimes. Maybe you can say S bigger than D, so dimension is D is the dimension of the space. When S is bigger than D, 1 over x to the S is integrable at infinity. And that's, you can consider as more a short range case. So in particular, you can sum pair interactions. This is also called hypersingular. Okay, and when S is less than D, then on the contrary, this is not integrable at infinity, and you should think of this as more long range. And this is what we're going to focus on. So in fact, I'm going to focus on S strictly less than D. And all cases of S positive have G singular at the origin. As you can see. So you cumulate kind of two difficulties, the difficulty of the singularity at a very short distance, and the difficulty of the long-range nature of the interaction. And particularly interesting is the Coulomb case. Which corresponds to the, the Coulomb interaction of electrostatics, for instance. Okay, so in dimension 3, which is the physical dimension, S equals 1, you recover 1 over the distance. In dimension 2, it would be minus log. In dimension 1, it will also correspond to S equal D minus 2, because it will be minus 1. And minus 1 here then comes with a negative sign due to the S in the denominator. Okay, so this is true in all dimensions. Mathematically, you can ask yourself, what is the mathematical characterization of the fact that you're a Coulomb interaction? One way to think of it is that then G is the fundamental solution to the Laplacian. Okay, because if you take minus Laplacian of G, it will be the Dirac at the origin with some coefficient, some constant in front that depends on dimension. which is just due to the fact we haven't normalized this in the right way in a certain sense. So this is a very particular case, but we will focus a lot on this because it's basically the best case to understand. So if you're interested in S between d minus 2 and d, so above Coulomb, but still in this sort of long range situation, then G is no longer the fundamental solution to the Laplacian, but G is the fundamental solution to what's called a fractional Laplacian. With alpha equals to d minus s over 2. So you check that when s is d minus 2, the alpha equals 1. And so this is consistent with the other one. And then here you can look up your favorite definitions of fractional Laplacian. So in the whole space, for instance, you can think of it in Fourier, right? It's the multiplier that would have the xi to the 2 alpha. When s is less than d minus 2, so this is going to allow us to do quite a number of things. And when s is less than d minus 2, there's not such a nice characterization, but if you want, you can get something with iterated differential operators. So then it would be iterated Laplacians and fractional Laplacians. Maybe fractional ones. So for instance, if you take d minus 4, it would be a square, a bilaplacian operator. So bilaplacian operator in terms of, as an elliptic operator is not as nice as Laplacian or fractional Laplacian. So this actually creates more difficulties, and a lot of the sort of theory I'm going to expose in this course is not completely finished in that case, although we believe it's kind of on the way. But this is, in some sense, when S is smaller, in some respects, things are a bit harder. So even though it's less singular at the origin, you always have this trade-off, right? If it's less singular, it's also more long range. So some things are easier, some things are harder, but this I would consider this rather harder. And you can even consider S non-positive, right? So then the sign of G in front changes. And as I said, in 1D, for instance, the Coulomb case falls in that category. But it's kind of makes sense to limit yourself to -2 from below, so to stop at x squared, because after that it's really a different kind of story. And there is some interest in looking at such negative cases, in particular in relation to statistics. So I will say a word about this maybe a bit later. Okay, so these are this is the class of interaction that I'm going to always consider, and now we can look at an energy. So we're going to have points x1 to xn, let's say, so a large number of points that live in space of dimension d, and then the energy for these points. Okay, we would want to take the sum of pair interactions. Sum of pair interactions between the points. So there is this repulsion, so it's always purely repulsive. In all the singular cases, points don't like to be in the same place. On the other hand, there's this slow decay that makes it difficult to sum such things when, if you wanted to take an n goes to infinity limit. Okay, so this energy on its own is not quite convenient to work with because you can immediately see that, for instance, if you want to minimize it, the minimum is not achieved. It corresponds to the points all just going to infinity, right? Because this, if g is positive, for instance, sending the points to flying apart to infinity will always kind of decrease your energy. So you need some kind of confinement mechanism if you want to work in all space. So we're going to add some what's called maybe a confinement potential, or also called an external field. Okay, so this is going to be, that's one way of doing it, let's say. So you can think of it as maybe the effect of some external force on the system. And what you want on your V is something like this, right? That V should go to infinity at infinity, such a way that it prevents the particles from flying off to infinity. Of course, there's other ways to create confinement, or you can also decide to work in the torus. So you can also, or in the manifold. So some people work on, the sphere, for instance, in approximation theory in particular. And you can also work on the torus, in which case you're going to have to periodize the interaction somehow. But that's okay.
So, yes. So when alpha is not 1, these terms are still conservative, but I guess in a different sense. So when I have minus, so a normal conservative force is minus lambda g, and then there's no work done in the loop, but when alpha is not 1, it's still conservative.
I don't think that changes. If you take gradient of g, it's still deriving from a potential, so that doesn't matter. It's irrespective of what the Coulomb is. Okay, so I want to now discuss. Okay, can I send this very high? Maybe not. Ah ouais. Ah, c'est manuel, d'accord. Je cherchais des boutons. Okay. Okay. Very good. So I want to discuss a little bit motivations for studying such systems, right? So where do things like this occur? So maybe you can think of it as just we want to do statistical mechanics, of so Coulomb or Riesz system. So Riesz is just a general case, right, that I'm discussing. And when we do statistical mechanics, we're going to look at situation at equilibrium with temperature and look at the Gibbs measure associated with this energy, right? So I'm going to denote it like this. All right, so this is canonical Gibbs measure. For later, I will use a slightly different temperature normalization. So here I'm going to multiply by n minus 1 s over d, which means that basically I'm going to divide the energy by n to the s over d, which is a natural length scale there. Another way of writing it is I'm going to consider theta equals beta n 1 minus s over d. And then the exponent is just e to the minus theta over n times the energy. So that's another way of looking at the scaling. So you look at the whole energy, you divide by the number of particles. So it's the energy per particle, if you want, and this becomes some new effective temperature. But OK, in the first pass, you can forget about that. Just say we have some beta, and this beta may depend on n. So we can choose different regimes. And so may theta. And so with that, you have what statistical physicists would call a Coulomb gas or a Riesz gas.
Can you explain why Hn divided by n is the energy per particle? Because if you look at the definition here, for each particle you have xi multiplied by n. So it should be something like n times the energy per particle.
But I'm not saying anything deep. I'm just saying I'm taking the energy and I'm divided by the number of particles. So it's the energy per particle. There's nothing.
Maybe my question is why you multiply this sum
by n.
By n.
Okay. So that's a good question. So this one is meant to sort of match this one, because here you have the sum of over all pairs. So you have n squared. You have n minus 1 terms. And so this one will give you n times n terms. And so this is to balance out. Okay, so the reason for this choice, of course you don't have to make this choice, but the reason is you want the system to be confined in a thing of size 1. If you put a different power here, you'll be confining in an n-dependent domain. So this is just to balance it out. So, okay, but of course, it could be also natural to divide. Yeah, so there's many different choices. That's why I'm saying you can all fit them into one framework if you allow beta to be possibly n-dependent, because it's not clear a priori what you should do. And so in some regimes, it's much more natural to take this whole thing divided by n. And that corresponds to that. That's the mean field regime in some sense. And the regime where you think of it like this is more like a low temperature regime. And each of them has their relevance in different situations. But so at first, I want to try to have a framework that can cover everything. Okay, so from the point of view of statistical mechanics, this is considered a hard system. So it's a hard model because, okay, it's not on a lattice, so it's not something that lives on. It lives in the continuum, sorry. And all particles interact with all particles. So it's very different from a nearest neighbor kind of model, right? So all pairs, and it's long range. So usually long range, plus it's singular. Okay, so for that reason, this have always been considered among the hard models. And they were very much of interest for statistical physicists because the Coulomb interaction is the fundamental interaction of nature, right? So a Coulomb gas like this can be seen as a sort of toy model for the interaction of electrons and, yes? What is what? Ah, yes, Z and beta. I should define. Okay, so Z and beta is called the partition function. It's what makes this a probability. So it's the normalization factor. Okay. So you have to divide by that to make it a probability. So that's always called the partition function. Okay, so toy model for matters. In particular in the Coulomb case. And in particular for plasma physics. So physicists, if you look at the literature, you will see this called a plasma, right? A Coulomb gas is one name, but a plasma is another name. So it's also called a one-component plasma. So I'm just saying that in case you try to search the literature, you will find this term one-component plasma. And why it's called one component? Because all the particles have the same sign here. They're all, let's say, positively charged particles. In contrast with the two-component plasma, which is a system where you have plus and minus.
I'm just wondering why you multiply by, or you just multiply by n to the minus s.
So I think this will appear later, the reason why, but this is a choice that makes basically the temperature beta, it characterizes the system at the microscopic scale, if you want. It's the effective temperature for the micro scale, whereas this theta is the effective temperature for the macroscopic scale. So it's just will be convenient later, but if you don't want it, you just can ignore this for now. In particular, if you're interested in the s equals 0 case, which many people are, then this just does nothing. Okay, so the one component plasma, or the Coulomb gas, there's a large physics literature in the 70s and 80s in particular. So I'm just gonna give some names, but there's people around Elliott Lieb, people around Jancovici, not far from here in Orsay. Martin, Philippe Martin, Alastuet. So I think Angèle Alastuet is preparing a book, or it should be out very soon, precisely on the Coulomb gas from a statistical physics perspective. So this is all 70s and 80s, and I'm going to forget many names probably, but more recently, Wigman, Zabrodin, and people involved in the organization here, Cher, Majumdar, and Dledoussal. So it's still a very active topic from that point of view. Julien also, you work on that. So maybe Julien is the one that has the most interest, I think, in we can explain to you why cases that are not Coulomb are also physically interesting. And these guys are also interested in that, so I think you'll hear about it more from Satya. So not only Coulomb is physically relevant. There's many reasons also to study Riesz. So this is one sort of direction. And another direction that's been quite productive is the connection with random matrix theory. There's also interest in approximation theory, but I'm not going to discuss that so much. Okay, random matrix theory. You can consider the simplest models of random matrices, which were introduced in particular by Wigner, Dyson, Ginibre. Okay, so let's say the original physical motivation was to describe the spectra of very large atoms, right? So like, when you have, that when you have an atom, it's interesting to study the spectrum of associated Schrödinger operator. So the idea was, well, let's think of an operator, of a self-adjoint operator, as just a very large symmetric matrix in n by n size, with n going to infinity. And what is the simplest law of the entries that you can think of? Well, let's make the entries IID and Gaussian, because that's step one, right? You make IID Gaussian entries for an n by n matrix. And so here, three choices. You make them just complex IID, or you make it real symmetric IID, or complex Hermitian. Okay, so in the first case, you have no symmetry imposed. In the last two cases, you have some symmetry imposed. So of course, you only draw sort of half of the matrix. So you draw only this lower diagonal part, and then you symmetrize. And then you compute the law of the eigenvalues. And that's actually exactly computable. And you find something that looks like that.
In the complex Hermitian case, the diagonals are real, so how can it be identically distributed as the other?
I can't hear you very well, but I'm exaggerating a little bit. What is your...
No, just this. Yeah. What is IID in the same case?
What is what?
IID, independent, identically distributed.
So it's IID on the... If you want, it's IID on the lower triangular part, and then you just symmetrize. It's more or less that. So it's not IID seen globally, but it's IID on the triangular. Yeah, the diagonal also. Okay, so this one is called the Ginibre ensemble. And so this is all n by n, right? And this one is called the GOE, Gaussian orthogonal ensemble, and this one is called the GUE, Gaussian unitary ensemble. So they're not really defined like that exactly, but I'm simplifying a little bit. And what matters is that you find a law of eigenvalues. So of course, for the complex case, the eigenvalues are going to be in the complex plane. And so you view the complex plane as R2, right? You identify the complex plane with the plane. So this one is on R2. And the other two cases, the eigenvalues are real by the imposed symmetry. So this one's going to be a law on R, and here also on R. And they all take the form e to the minus beta Hn. So they all take the form of exactly a Riesz gas that I will call here a log gas. So we're in the log case. So S equals 0 if you want. And V is quadratic. So it's some constant times x squared. And beta is a very special value. So it's 2 for Ginibre and GUE, and it's 1 for GOE. So another way you can rewrite this is that because you have exponential minus, let's say 1/2 sum of minus log xi minus xj, right? plus n, let's say something like that. Of course, you can decide to take the log down inside the exponential, and so you find that this is going to look like a product. Something like that. And here you're going to have some sort of Gaussian terms. Right, so you see that what arises inside the Gibbs measure takes a very particular form. In this case of logarithmic interaction, and you recognize here a von der Monde determinant, and this is not coincidence in some sense. And so these particular cases are called determinantal. Because they belong to a wider class of laws that arise as determinants of stuff. So I will expand a little bit in a minute. Yes?
So it might be trivial. So why is the Z 1 here? Is it just trivial?
I forgot the Z, yeah.
Oh.
Thanks. All right, so if you want, there is a sort of intersection of this Coulomb log Riesz gas business with random matrix theory, right? And they cross at this particular case for these very particular values of betas and the log interaction, quadratic confinement. But random matrix theory is much broader. It also considers much more general laws than Gaussian here, right? So you might want to generalize that, but then you're really going in the transverse direction. And in our situation, we're like wanting to generalize away from beta equals 2, for instance. We want to look at all betas, and we want to look at all dimensions, not just 1 and 2. And it happens that at this crossing point, you can compute a lot of things. So a lot of things is known thanks to this sort of random matrix underlying structure, and thanks to the determinantal structure, a lot of things can be computed very explicitly. So this gives us a lot of information about one very particular case. But this can serve also as a sort of test bed for more general ideas. Okay, so you can say that basically here everything's understood. Okay, so historically this has been very much studied, completely understood, and people also were very interested in the one-dimensional case for that reason, because of the GOE and GUE. So this is a situation where 1D has been much more studied than 2D, which has been still much more studied than anything else, I would say. So 1D is particularly interesting, or particularly studied. People have immediately generalized the log gas. So 1D log gas for general beta is also called beta ensembles. I don't know why, but this is the name that has stuck. So when you see beta ensemble, you should think it's a 1D log gas, but with general beta. And now this thing, turns out there's also a matrix model underlying it. So there exists a random matrix model. It's not as simple as GOE and GUE. It's a sort of tri-diagonal matrix, random matrix model, and thanks to that you can also compute some stuff, although not as much as the other one. In 1D, there's a lot of things and also the 1D Riesz gas has been a bit more studied than higher dimensional things. So people also studied on the circle, as I said. And so on the circle here, it goes with the name C beta E, circular beta ensembles. So here you also have a circular Riesz gas where you periodize the Riesz interaction. And this has been particularly studied recently. There are some very nice results by Jeanne Boursier. I'll state some of the things she proves. And in all these cases, you notice that you have some things in 1D that you will lose as soon as you go to higher dimension. First is you can order your particles, right? You can decide what's the leftmost and what's the rightmost, and you can sort of label them. So particles are ordered. In 1D, which you lose in higher dimension, and that's, you know, that makes things more complicated. And the other thing that's very nice about 1D is that the interaction is convex. So when you look at what it is in 1D, even though it's singular, it's convex, and that you will also lose in higher dimension. So for that reason, you can hope to do much more, and much more has been done in these 1D settings. Okay, and finally, in terms of other motivations, I want to mention that the 2D, so the 2D Coulomb case, which is also the log case, as I told you, it's also called a two-dimensional plasma. So sometimes it's called, like in physics papers, you'll find this acronym for two-dimensional one-component plasma. So it's been studied not only because of its relevance for plasmas, but also its relevance for many, or a certain class of quantum mechanics problems. But that's also true in 1D, by the way. So free fermions and things like that, when you look at their wave function, you find things that look like that. And in particular, another thing that's particularly interesting is the quantum Hall effect, a fractional quantum Hall effect. So in all these sort of quantum mechanics problems, you're looking at wave functions, and if you look at the modulus squared of the wave function, you can put it in one of these boxes, in particular in the 2D Coulomb case. And so there's been a number of studies basing themselves on that. Okay, so for that reason, again, 2D also has been quite studied. You have this Ginibre ensemble. 3D a little bit because of the relevance for, you know, general ambient space classical physics. And higher dimensions, much less, right? General Riesz, higher dimensions, there's much less. So this is the general picture of motivation. Do you have any questions at this point?
So maybe you mentioned about ways to so a confining potential, or put it on a periodic coordinate. Yeah. You can also do a naive thing of maybe screen interactions. So in physics, I guess you do something like device screening.
Yeah, so then you can tweak the interaction itself, really, right? Yeah, so you can replace G by a Yukawa kernel, for instance.
With something really long decay.
Yeah, but then you know you're treating a different model, and then you'd have to show that it has some relevance for what you wanted to do in the first place. So yeah, it's possible, but okay. So I want to talk about the kind of questions now that you can ask. Okay, so first question, if you present things like that with the confinement potential, etc., is what is the distribution of the points looking like? At let's say at a macroscopic level. Right, so another more mathematical way of phrasing this is I want to look at the empirical measure of the points, which is a random object, right? It depends on temperature and stuff. And I want to know if there is a limit for this and how this thing depends maybe on the elements of my problem, so G, V, the temperature, etc. So that would be the sort of also mean field limit regime. And then I would want to see something about next order and something about more microscopic distributions, right? So what can we say about, so let's say this difference, right? Does this thing have some kind of limit? You can call that fluctuations. So one of the way of trying to describe this is to take some test function, for instance, and see if this thing has a limit. Well, in the first pass, you can try to do it for smooth test functions. Right? So you look at smooth test functions, you try to see if this thing. Yeah.
Here you mean a limit in n or in some other parameter?
N, yes, thank you, n. Very good. Good point, thanks. So I want to take the limit as the number of particles goes to infinity. In principle, I'm fixing my beta or my theta, I don't know. This is all to be determined, but the rest is fixed, you know, G and V. So you want to understand things like that, for instance. So this would be called also linear statistics fluctuations, because if you look at this thing, it's also the sum of phi of xi, right? So it's called smooth linear statistics. One that's very interesting is to take the indicator function of some set. So some set omega, or maybe a ball, just a ball. So you're going to have your Coulomb or Riesz gas, right? And you're going to look at a certain window of it. And that's your omega. And basically what you're trying to do here is count the number of points that fall there. And see how different it is from the integral of that mu. Right? So what's the fluctuation of the number of points, or it's also called charge density fluctuation. And you can try to do that for omega that maybe so has macro scale, or maybe mesoscale, or maybe micro scale, right? So I need to explain maybe here what I mean. Okay, so the situation here has been that we have made it so that the particles are confined to region of size 1. Right? This is how it's been set up. So this is the region, let's say, where most particles are. And so you have n particles here. And this is of size 1, order 1. All right, so what's the typical distance between particles? Well, there is basically n boxes in a thing of size 1. So let's say each particle occupies a box. So each box has volume 1 over n. And so the side length of the box is 1 over n to the 1 over dimension. Right? So this is n minus 1 over dimension. That would be the typical interparticle distance, for instance. So this is the microscale. Right, so this is the microscale, and this is the macroscale. And then in between, you can look at other length scales, like, for instance, other powers, and n to the minus 1 over d, so n to the minus epsilon, for instance, is a mesoscale. Right, so you can start to play with the size of this red window, and you can try to decrease it and see if you can say things down to the microscale, and that would be the ideal, right? If you can say things more and more precise, or at least at smaller and smaller scale. So in particular, in this question of counting number of points, I will mention a result already. I should not have done that. Okay, let's see. So the physicist Sal Torquato introduced this notion of hyperuniformity, which is basically saying, okay, if you have a point process, so all these things behind you have point processes, which are just random point configurations, if you want, or random infinite point configurations, or more mathematically, laws on infinite point configurations. So you say that a point process is hyper-uniform if the variance of the number of points in a box, the variance of number of points in a ball of size r, let's say, is much smaller than the variance for the Poisson point process in the same ball. So it should be basically that the variance of the number of points is much smaller than the volume of the box. So it depends on how you normalize things here. Things are normalized in such a way that there is 1 point per unit volume. So you take this picture and you sort of zoom it out, and the density of points gets normalized to 1, let's say. Okay, so it was a sort of conjecture, you could say, for a long time, that the 2D Coulomb gas is hyperuniform. So this was proved quite recently by Thomas Leblay. So he proved the full thing that the 2D Coulomb gas, so it's only Coulomb and it's only 2D. Huh? Hyperuniform for all beta. So in the regime of temperature I discussed. And this generalized what was known for beta equals 2, because I told you from before that beta equals 2 is the determinantal case. In the determinantal case, you can compute stuff. And so in particular, this was known when beta equals 2. But now it's true for all betas. And it remains a completely open problem to know if this is true in higher dimensions and if this is true for different Riesz interactions. It's not clear. It's not clear. So there's a whole line of thought of people who ask themselves these kinds of questions. Yes?
What is the motivation between the name? Why hyperuniform?
Why do you call it hyperuniform?
Why should they be interested in saying that something is hyperuniform or not?
You know, there's a sort of general question of build point configurations where the points are well distributed. You know, very well distributed points. Okay, so your first guess is like, oh, well, take a lattice. I mean, this is going to be very well distributed. But people want to find things that are a bit less rigid. So they want to expand what's beyond between a lattice and a Poisson point process. A Poisson point process is you just throw the points at random uniformly. But you want something more ordered where they sort of don't sit too close to each other because the Poisson points can just be on top of each other. So that's when they get interested in these determinantal point processes that have some good features. And then hyperuniformity is this idea that it's going to be something in between. It's going to be quite well ordered, but not as ordered as a lattice. And the way they think of it is they think of it in the Fourier space, right? They look at what they call the structure factors. They compare the cancellation of the Fourier coefficients with what you would see for a lattice, what you would see for a completely random thing. And so that's all I can say about the name, but it's not my name. So, yes?
What happens in 1D?
So in 1D, in 1D, you completely understand the limit point processes for the log, and you can compute, indeed, it's also hyper-uniform. So yeah, I'm going to, actually, it's a good point to say something about 1D. But so maybe first, I want to say that together with all that, there's a natural question is find local limits. What you can call local limits or limit point processes. So what that means is now I want to take this picture which has many points, right? And I want to zoom in near a point and then look at things. So you multiply everything by n to the 1 over d, and then your points become separated, distance of size 1. And you want to see if there's a limit to that sort of configuration that extends all the way to infinity. And that would be this sort of random point process or limit point process. Or if you want limit of things like n 1 over d delta xi or just xi. Right? So this sort of family of points. And can you characterize them? You know, what can you say about them? First, do they exist, such limits? So again, to show you the extent of our ignorance, we don't know to prove in the general setting that there exists a limit point process. It's only known in these very particular cases that have this determinantal structure, or it's known up to extraction of a subsequence. So you don't know that there exists a unique point process. There exists a limit point process, but there could exist several. So let me say a word about what's known. So in 1D log, so when beta equals 2, there's a limit point process which is called the sign process. So it's a determinantal point process. And now it's time maybe to say what is a determinantal point process. It's a process in which you can express all the k-point correlation functions in terms of determinants. So first, let's look at k-point correlation functions. Called rho k, maybe x1, xk. So these are essentially like the limits as n goes to infinity of the k-point marginals of your law. So it's like the probability of finding points, points at x1, xk. So the 1-point process is just the probability of finding a point at x. The 2-point process is the probability of finding a pair at x1, x2, etc. So what you could do is you could just take an integral of dpn beta xk, xk plus 1, etc. to xn, and you integrate with respect to the last variables. Okay, so that would be rho k, still depending on n. So that's what I mean by the k-point marginal, and then you can take the n infinity limit, and you call that rho k, right? So in this particular thing, you're already at the limit. There's an infinite number of points, and the k-point correlation functions for a determinant or point process, they can always be expressed as the determinant of some matrix that takes a form like that. And here, I and j go from 1 to k. Okay, so it's a k by k matrix, which has entries depending on a certain kernel, capital K. Okay, so for each kernel, you have a determinantal point process. For each determinantal point process, you need to have a kernel. And in this particular case of the sign process, it's this, where the kernel K is of this form. So it's this well-known function. Okay, so this is the sign process. And now you see you have a recipe for computing all your k-point correlation functions. In principle, you just have to compute these determinants, and you can see how the correlations decay. And this is actually one of the most desirable things to understand among these questions, is can we understand decay of correlations? Because in physics, decay of correlations basically tells you the state of matter. Decay of correlation, right? Depending on how fast you decay, you're in a solid, or you're in a liquid, or you're in a gas, more or less. So, if I'm not mistaken, yes, so a transition from liquid to solid, for instance, you can see it as going from algebraic decay of correlations to no decay, and I think a gas to a liquid would be going from exponential decay to algebraic decay. So these things can be observed in 1D in certain situations, but we have very poor understanding here, at least on a rigorous level. Very poor when it comes to rigorous results. So this is the sign process, and there is another sort of cousin of it, which is the beta equals 2D, s equals 0. So the log case or Coulomb case in 2D, that's called the Ginibre ensemble. I told you this is another case that's determinantal. And then there is another exact kernel whose form I don't remember by heart, but it's essentially an exponential kernel. So I'm not going to write everything, maybe, but it's something like this. There's some pi's. I don't No, and then there's a sum of z w bar L. Okay, so there's like some exponential and exponentially decaying kernel that gives you all the k-point correlations, but it's only for beta equals 2. And then aside from these determinantal cases, there's been progress in 1D. So 1D log again. So this is also called beta ensembles. It is known that there exists a limit point process. Again, it's unique. Huh? That's called the sine beta point process. So they called it sine beta, well, by generalization of the sine point process, right? It's called the sine beta point process. And this was introduced and characterized by Valco and Virag, and Coulomb and Stoicu. I mean, mathematically, rigorously. Coulomb, Stoicu did the circular case. And for the sine beta point process, you don't have a determinantal structure. You don't have a kernel. You have a much more indirect characterization, which involves the solution of some stochastic differential equations. It's a bit mysterious, and you try to extract information from that formulation. You can get information about the size of gaps and things like that, but it's not easy, so very indirect. But at least there is existence and stuff. There's also characterization now by De Reudre, Lambert, Hardy, and Maida. De Reudre, Hardy, Maida. There's a fourth one, I'm not sure. And another case recently understood is the beta circular Riesz gas. And that was done by Jeanne Boursier in her PhD. Right, so you have a limit, and it's not up to extraction, it's a real limit. So you can call it a Riesz beta point process exists. And this is 1D, of course. Huh? So it's on the circle. And she's also able to get a central limit theorem for the gaps and the discrepancies, the variance of the number of points. So maybe I can say something about number of points in an interval, the variance of that. So this is completely understood in the log 1D log case, and the variance is in log n. And in this 1D Riesz case, she shows that it's in n to the s. So you see, when s goes to 0, you can't quite take the limit and refine the other one. So I think that was to answer a question about what's known in 1D. But you see, there's a really very wide field of open question, which is find the existence and the characterization of point processes in all dimensions beyond the beta equals 2 log case in 2D, for instance. So now the kind of results we have, and I can mention maybe a result by Eric Thomas. So there exists a subsequential limit point process. So for the Coulomb gas in the Coulomb gas in any dimension. So the way to do that, what this question really is you want to look at these boxes here, but microscopic boxes, right? And you want to just show that in a microscopic box, your number of points becomes essentially bounded. Typically, you know, when you look at the micro box, now you only see a finite number of points, not divergent with n goes to infinity. And if you can do that, then by some sort of compactness argument, well, you extract a limit. You know, that's it. But so the hard part is to find that the number of points is bounded. If you're allowed to extract subsequences, that suffices. Yeah, so that's what it does. But for now, it's only for Coulomb. So it's not completely clear that the limit point process or early limit point process should always be unique. In fact, it's probably the case that if you have a what's a phase transition in physics, then you will have a non-uniqueness at that particular beta. So, okay, so the question is another question. Again, we don't have good answers. Is are there phase transitions? Right, so if you look at beta, is there some sort of beta critical below which, I don't know, I have maybe exponential decay of correlations or something like that. And here algebraic decay means inverse power. Algebraic means inverse power. Like, is there a picture like this? So in 1D, it's not the case. Because in 1D, we can compute a lot of things. So 1D log, it's not the case. But in 2D log, in the 2D log situation, there's a number of physics papers that tell you that there is a transition like this. Right, so 2D log, transition predicted. So in the one component plasma, in some physics papers, and it's not so much that it's predicted, I would say it's numerically observed. It's not, they don't really have what I can read as a heuristics or some vague computation. It's just run the numerics and see that something seems to be happening. By the way, this beta C is something around 50, or there's like some number. And it's, I would say it's controversial, even within, you know, among physicists, not everyone agrees that there is such a thing. But that's very mysterious. It would be very interesting to be able to see something like that, but we're very far, because I told you we don't really have a good handle on the correlation functions.
Sorry, can I ask you?
Yeah.
But why it is mysterious? It sounds like a BKT transition. So we can reformulate slide model in terms of...
Yeah, but the BKT transition is in the two-component plasma, the one where you have plus and minuses. Okay, so this is for the one component. You don't expect the same kind of transition. So yeah, in 2D, in the case where you have plus and minus charges, you're going to have actually two transitions in some sense, but you're going to have a transition where you go from a completely disordered state to a state where particles pair as dipoles. But this is a different model. And another I'm going to finish with two more sets of questions. What was my other set? Yes. The questions of universality. So, for instance, in random matrix theory, people have asked themselves a lot this question. If you draw your entries to be IID but not Gaussian, are you going to find the same in the end as when you draw them Gaussian? Because when n goes to infinity, you know, maybe certain limit things are universal. And they found that, yes, if you have a certain number of moments, it's the case, right? And so here you can ask similar questions. For instance, if you change your V, are you going to see things in the local limits, you know, the same as if you take V quadratic, for instance, right? So are things universal, or maybe at the local scale? Universal with respect to V. Is it true in all dimensions? And a big, of course, a natural question from this whole perspective is how much do things depend on G, right? It's like, are there features that are the same all across the different Riesz cases? So in 1D, there is this particular work of Bourgade, Erdős, and Yao. So in the 1D log case, which again is the most studied, really the most studied case. So Bourgade, Erdős, Yao proved universality of, for instance, gap fluctuations and things like that with respect to V. And it's very natural to expect that at the micro scale, things are not going to depend so much on the particular macro characters of your system. And the final thing I wanted to mention, and we're going to discuss it quite a bit, is free energy expansions. So here what you would like to understand is the free energy. So the free energy is defined as -1 over beta, the log of the partition function. So if you think of it, you look at what Zn beta is, it's integral of exponential of an energy. So if you take a log, this is what's called the free energy. And you want to understand this as n goes to infinity. So in particular, you want to understand if there is a sort of expansion in n. All right, so I'm going to simplify here a little bit, but so here, in the way that I wrote it, there's going to be a leading order term that's n to the 2 minus s over d, and then the next order term, maybe n, or then there's maybe some log n term. Okay, so you expect some expansion of the free energy with powers of n that sort of jump. And the coefficients here will still depend on beta. And in truth, when s equals 0 and d equals 2, so this is one of our beloved models, the 2D Coulomb gas, there is even some very precise predictions. I would say predictions in physics. So Forrester and Wigman and others that say that there exists such an expansion. So when your s equals 0, so it's really going to be n squared, and there's an n log n, I think. There's an n log n term that's explicit. And then there's n, and there's log n. And they tell you things about these coefficients, and the coefficients in front have very interesting geometrical content. So they relate them to quantum field theories, in fact. And so for us, as a mathematician, the question is, can we describe these coefficients? Can we understand how they depend on V, for instance? Is there such an expansion, of course? And what I can tell you is that the leading order coefficient, that one is easy. So we'll see it very quickly. You can compute the coefficient in front of n log n, that's also easy. And the thing that we're able to obtain that I'm going to describe in these lectures in particular is the next order coefficient here. So we have access to this in fairly general Riesz context, but anything that's beyond is completely open, at least for a proof. Except, of course, one dimension, because I told you in one dimension you can compute a lot of things, or much more is known. And this is you have expansions to all order, provided, okay, let's say for simplicity that maybe V is analytic. So that's a little bit restrictive, but okay, for V analytic, I'm sure it's completely proven, and there's particularly results of Sherbina and Boro-Guyonnet doing that. I may be forgetting some, but. And what we're going to see is that the coefficients here really also contain some information about the microscopic structure and behavior of the system. So it's not just a curiosity, I would say, to explain these expansions. They are really intimately tied with understanding all the other questions. So these questions are not independent. Yeah?
Sorry, do you know that this expansion exists for S between t minus 2?
In general dimension?
Yes.
So no, in general dimension, what we can prove is that there is the first two terms, if you want, plus little o of something. So we don't know a full expansion. We know two terms with a remainder. That's quantitative. But of course, in 1 and 2D, S equals 0, you know more.
Do you know anything for when S is smaller than 3?
No. So that's probably doable, but that's not yet written as far as I know. And of course, yeah, beta equals 2, D equals 2. In some, you know, in the case where V is quadratic, then you know from the determinant all case. Any other questions?
Is this related to sort of, in physics, you do sort of a virial expansion? So the question is, the physical meaning of this B beta, it's some sort of like virial coefficient, contains some sort of...
Not sure.
Okay,
I'm not sure.
What's the meaning of beta?
Geometrically? So the kind of things we can get are just formulas that express a little bit of the dependence on V and on what's called the equilibrium measure, which I'm going to define in a minute. So that's one geometric interpretation. The reason why people think of it geometrically is that they think that, okay, if you give yourself a V, that's going to give yourself a sort of background density. And that density is equivalent to fixing a metric. So that's why they think of it as a geometric quantity. So maybe it's time for me to stop. No, what do you think, Isabel?
10 more minutes.
I have 10 more.
Well, you started late, so.
Okay. So I can use 10 minutes. It's good. I thought I had only 3, so then. All right. So this is the sort of general introduction, and I think it's just to give you a taste. I'm going to be very disappointing because I cannot answer most of the questions that were phrased now, but let's look at a few things we can say. So in particular, we're going to immediately discuss what is this limiting density associated to the system, which is not too hard to find, and that's called the equilibrium measure. So you start again from your energy, right? So if you remember, there's a sum of pair interactions. And I'm going to rewrite this in integral form, if you allow me. in terms of what's called the empirical measure. There should be a D here. Okay, so if you expand this, this thing and you put an n squared in front, okay, you should see that you refine your sum of g of xi minus xj, provided you put a 1/2, and provided you remove the diagonal. So here, we're going to denote this triangle for the diagonal in RD cross RD. So this corresponds to the fact that you take xi, I different from j. And then the other part is just the integral of v okay, so this is all now expressed in terms of the equilibrium, the empirical measure. So let's call that mu n, maybe mu n, or maybe with a hat, like empirical, right? And so now you naturally can expect this to be related to the following function, which is just I take that and now I do it over the class of all probability measures. Right? So now this is from mu a probability measure on RD, which is such that this thing is finite. I mean, not all measures are going to give a finite answer. And note that here I don't remove the diagonal anymore. Okay, so this is functional. So it's this or plus infinity if the integral is not convergent. And now this function is much nicer than the original one because it's convex. You can check. And the theorem is that under assumptions of v on v, so if v grows sufficiently and it's lower semi-continuous, then this E has a unique minimizer. And so here I'm restricting myself to S less than D. Huh? S less than D. I told you I'm only going to talk about that. And you can immediately see that you need S less than D because this is like 1 over x minus y to the s, right? And if you want this to converge, even if mu was a very nice measure, like smooth, you need s to be less than the dimension. Otherwise, you have divergence in the diagonal. Okay, so this is one place where you see immediately the long-range nature. Long-range nature is what allows this thing to even have a meaning. So this has a unique minimizer, so it's called the equilibrium measure. So sometimes it's denoted mu v or mu ek. There's different. It depends on v, depends on g, obviously. It has compact support. That's if v grows sufficiently fast. And it's uniquely characterized by a set of equations and the set of equations is this. So I'm going to define my notation. So there exists a constant c. So that's part of the characterization, right? There exists some c, some number, such that defining h mu as the potential generated by mu. So it's the convolution of g with mu, right? So this thing plus v is bigger than the constant everywhere. And it's equal to the constant in the support of mu v. So you should think of these things as the total potential, right? So you have mu v, a distribution. Think of it as a distribution of charges. think of h mu v as the sort of electrostatic potential generated by the distribution. So it's the sort of self-induced potential. And then think of v as the external potential. So you add the external and the self-induced potential, and these things have to be constant where there are charges. And outside it has to be larger. So this is really an old problem in potential theory that was studied by Gauss even. So it's like the capacitor problem in some sense. And the characterization is this, and it's not very hard to prove. If I had more time, I would prove it for you, but just take mu, which is the optimizer, and then change mu into 1 minus t mu plus t nu, where nu is arbitrary and t is in 0, 1. And say, okay, this guy has a larger energy E than that guy. Then expand in t, and you'll find all of that.
Support of nu?
Sorry?
Support of nu?
So nu is an arbitrary measure. Now this guy mu v, the support of it, it's part of the problem. It's an unknown. Right? So there exists a support. It's a measure with compact support. This support is some set. You don't know it as it's just part of the equations. There's a unique support. There's a unique
support?
Yeah. So the support is part of the problem. Okay. So let me give you examples. So you can actually study this problem from a PDE point of view. And you can characterize the support differently, but example, that's the maybe most basic, most important. If G is Coulomb, and if V is, say, quadratic, so everything is rotationally symmetric, you expect your equilibrium measure to also have this rotational symmetry. Then mu V is an indicator function of a ball. And so you have to normalize. And the size of the ball depends on the constant you put here, but let's say the unit ball. So in this case, the equilibrium measure, you see, it's just going to be uniform density in some subset, which is the ball. And in random matrix theory, this corresponds to, this matches what's known for the eigenvalues of the Gillibrand ensemble and all of these, which is called the circle law. I'm reaching the point where I should probably stop. But the circle law says that precisely your particles are uniformly distributed in a disk. Another example is G equals minus log in 1V, and V is quadratic. Then mu V, some constant times square root 4 minus x squared, indicator of x less than 2. So this is what's called the semicircle law. So if you plot this thing as a function of x, it's like that. This is the mu v. This is minus 2. This is 2. This has exactly the shape of a semicircle. And if you look at the histogram of eigenvalues in the GOE ensembles, they follow exactly this type of distribution. And so you see now it's different. So here the density jumps. Density jumps from 1 to 0. That's the Coulomb case. Semicircle law, the density vanishes like square root. And actually you can show that in the Riesz case, in general Riesz, you have an equivalent of the semicircle law in 1D. And in general, you're going to have vanishing like distance to the boundary of the support to the power 1 minus, so it's 1 minus d minus s over 2. So if you're in dimension 1, s equals 0. This is 1/2. You recover what we find for the semicircle law. If s is d minus 2, you recover distance to the power 0. So it matches the jump here. So there's a fairly general facts. And you can recover all these facts by mapping. Basically, there's a one-to-one correspondence between your equilibrium measure problem and a fractional obstacle problem in calculus of variations in PDE. And that correspondence is only true for S between d minus 2 and d. But when you're in that interval, so more singular than Coulomb, less than d, you have this fractional Laplacian representation for g, then a lot of things that you might want to know you can import from PDE literature and the fractional obstacle problem. So I invite you to look, if you're interested in those questions, and in general, I invite you to look at two very interesting surveys. In particular on these equilibrium measures, there's a survey by Jalil Shafai that's called Aspects of Coulomb Gases, I think. And on the general Riesz problem and all these questions, there's a very nice survey by Mathieu Levin also. That's called Riesz, the known and the unknown. So there's even more questions than what I mentioned. So now it's probably time to stop, and I think I'm getting to my end. Thanks.